Welcome to the Explainer, guys. Let's get right into it, because today we are diving headfirst into a fundamental rule of the universe, the action-reaction force pair. Now, it's a concept we experience literally every single day, but it actually holds some pretty surprising paradoxes when you really break it down.
So let's kick things off with one of those paradoxes. You know the old rule, if every action truly has an equal and opposite reaction? Why doesn't a fired gun fly backward just as fast as the bullet flies forward? It kind of breaks your brain for a second, right? It seems to totally contradict what we think we know about physics. Well, let's see if we can crack this mystery together.
To figure this out, we're starting with section 1, when two objects interact.
Let's unpack this with a super relatable, everyday scenario. What happens when you just place an object, like a coffee cup, on a table? It just sits there. It looks completely static, right? But actually, there is a constant, silent interaction taking place right under our noses.
You see, there are actually two distinct forces resulting from this interaction, and together they form an action-reaction force pair. First up, the action force. The object itself exerts a downward push onto the table. But simultaneously, there's a reaction force. The table exerts a push right back upward onto the object. And notice the juxtaposition here. The magnitudes, or the sheer strength of these forces, are exactly the same, but their directions are exact opposites.
Which leads us to section 2, defining the third law.
We all remember this from high school, right? Newton's third law of motion. Every action has an equal and opposite reaction. It carries a lot of weight in the science world. It essentially means that whenever two objects interact, there is an equal and oppositely directed force placed on each of them. Period.
So, how does this scale up? Let's jump to section 3, action and reaction in motion.
Let's look at the mechanics of a swimming frog. When a frog is navigating a pond, the initial action force is exerted by the animal physically using its little legs to push the water backward.
And boom, here is the immediate equal reaction force. Because the frog pushed the water backward, the water instantly pushes the frog's body forward. It's actually the reaction force from the water itself that provides the frog's propulsion.
But what about when things seem a bit more empty? Does the third law apply to a bird flying upwards in the open sky? I mean, at first glance, the bird really appears to be the only object in this scenario, just existing up there in empty space. But there actually is a crucial second object to interact with. The air itself is that second object. The bird's wings push the air downwards, that's our action force, and in immediate response, the air pushes the bird upwards, our equal and opposite reaction force. This invisible pairing is literally what makes flight possible in the first place.
All right, now we are ready for section 4, the gun recoil paradox. Let's solve our opening mystery.
Firing a weapon is actually a flawless display of this law. A fired gun exerts a massive forward action force to propel the bullet out of the barrel. Simultaneously, the bullet exerts an absolutely equal, entirely opposite reaction force right back onto the gun. And that, my friends, is exactly where recoil comes from.
But this brings us right back to our climax question. If the magnitude of the force exerted by the bullet on the gun is the exact same as the force exerted by the gun on the bullet, why on earth doesn't the gun recoil into your shoulder with the same massive acceleration? We have identical forces, but wildly different accelerations. What gives?
Okay, the missing puzzle piece here is Newton's second law. Let's trace the steps. First, force is the product of an object's mass multiplied by its acceleration, right? Well, step 2, let's just flip that algebra around. Acceleration equals force divided by mass. So step 3 gives us our ultimate conclusion. Greater mass means lesser acceleration. Mass fundamentally dictates acceleration.
When we compare the gun and the bullet side by side like this, the key variable becomes super obvious. The force applied to both of them is completely equal, but the mass of the gun is much, much more than the tiny little bullet. So, as dictated by the second law, that massive difference in mass is exactly what causes the huge difference in acceleration.
To really cement this, let's look at one final analogy. Imagine you're stepping out of a small rowboat onto a dock. As you step, you push the boat behind you, and the boat pushes you forward. Because that small boat has pretty low mass, it's visibly pushed really far back into the water. Now, compare that to a sailor jumping off a massive, incredibly heavy cruise ship.
The sailor applies a force to the ship, and the ship applies an exact equal force right back to the sailor. But based on how force, mass, and acceleration all interact, Will that giant ship accelerate backward as much as the sailor jumped forward? I think you know the answer now. Keep the reality of mass in mind the next time you see an action-reaction force pair out in the real world.